So today's notes are Unit 3. It is not in the textbook, but it does relate to our unit because it's talking about another measure of spread. So again, the coefficient of variation is a measure of spread that describes the amount of variability relative to the mean, similar to the standard deviation. Because the coefficient of variation is unitless, doesn't have units on it, you can use it instead of the standard deviation to compare the spread of data sets that have different units or different means. Here's the formula. So if you're dealing with a sample, CV is our abbreviation for coefficient of variation, capital C, capital V, equals standard deviation divided by mean for a times 100. That's for a sample. Notice the only difference is going to be the letters. We have an S and an X bar versus a sigma and a mu for population. I forgot to put in here times 100, so add that in because it is expressed as a percent. Super important. Here's an example. Let's just say that you are a quality control inspector. That's a real job. So somebody that goes around and tests batches of things to make sure the standard is still being met within a small amount of variation. And your job is to test milk bottles. You've got small and large milk containers. You take a sample of each product and observe that the mean volume of the small containers is 1 cup with a standard deviation of 0.08. In a larger container has 1 gallon or 16 cups for the mean and standard deviation 0.4 cups. So we see here there's a 5 times greater standard deviation for the larger container than the smaller container. If you multiply this by 5, you get 0.4. Let's see what happens when we look at these without their units. So we're going to do the coefficient of variation for the small container, dividing sigma by x bar. So sigma is 0.08 divide by 1. So this is cups and cups times 100. Notice what happens if I divide cups by cups. Units go away, and I have 8%. So the coefficient of variation is 8% for the small container. And the coefficient of variation for the large container is going to be 0.4 for the standard deviation divided by 16 times 100. Go ahead and calculate that one. What'd you get, Andrew? What did you get? 2.5 is correct. 2.5%. So did you do 0.4? Divided by 16. What did you get?
I got 2.5.
Okay, good. Because that's what we should get. And notice now, although it looked like there was a much larger standard deviation for the larger container, it turns out when we kind of standardize those, we take away the units, that the standard deviation is actually more significant for the smaller container because we kind of converted that, took away the units and kind of took the mean out of the equation.
So is this often only used to compare two numbers that are different units?
Different units of measure or different means, yes.
Okay.
And that's what it says actually in that sentence up there.
Okay.
So good, yes. So we're going to practice. Question number 1. A set of data has a mean, x bar, of 88 and a standard deviation, s, of 11. So we're just going to do CV equals 11 divided by 88 times 100. I'm going to go down the line, so be ready to answer. Everyone should have a calculator. Oh,
So what do you mean? What line are you gonna start at?
be ready.
Okay.
Courtney, coefficient of variation for number 1. 12.5%. Anyone second that? Excellent. Anna, we're going to get you next, so be ready. CEV for our second one. So we have the X bar is 1200. Standard deviation is 12. 12 divided by 1200 times 100. Anna. One what? Help her out. Christian.
1%.
Good. Percent. Remember, it's expressed as a percent. Important to keep that in mind. Number 3. Alexandra, what'd you get? 11.1? 11.1 what? Yes. Next, something is wrong with number 4. Or different, I should say. I could label the X bar, but then I have variance. What is the symbol that we use for variance? Layla? Sigma?
No.
Mu is looks like a U.
That's mean of a population. Variance is S squared.
Oh, I didn't know that it had those things.
That's between 6.1 and 6.2 nodes.
Yeah.
Nailed it, yep. So we have X bar is 118, S squared is 36, so S is the square root of 36. So read carefully, yes. When you're doing questions, it's always important to read carefully. I feel like in stats class especially, it's easy to overlook some key things. So now we calculate this one, which is, let's see, 6 goes on top, 118 on the bottom, times 100, justice.
5.001, no, 5.1.
5.08?
Yeah.
Okay, we'll take that.
Okay.
And last one. Be ready. It's coming at random, your direction. Again, we have S squared, so be sure to convert that. Phoenix, number 5. Layla. 0.41%. Okay, so this is coefficient of variation. Make sense? Cool. Flip it over. Little review of some distribution shapes. Speaking of measure of spread, this is more focus of measures of center. Okay? 2 key things we use to describe data sets in statistics. So for distribution shapes, we have negatively skewed, positively skewed, and normally distributed. Negatively skewed, little whale picture, maybe I hope you remember. The tail is on the left side, in which case the mean actually falls to the left of the median and the mode. Those are some important thoughts to have committed to your memory. It kind of makes sense if you think about there's this tail on the left-hand side, so it spreads in the left direction, so it makes sense that there's like an outlier, some data points that are smaller than the rest, so that's going to kind of pull the average to the left. And conversely, if it's positively skewed, you've got the tail on the right side. It's also called right skewed. And that would mean that the mean falls to the right of the median and the mode. Recall that the mode's going to be the highest bar, right? That's the one that has the most frequency. And then finally, for the normally distributed or bell-shaped curve or symmetric distribution, mean, median, and mode are all equal, right in the middle. So no whale for this one. Tried to make it work. Just plain old bell-shaped curve. I could have done that. Next time. I'll be facing each other. Okay, here's your examples. Take a look at A, B, and C and try and decide if the data is skewed left, right, or normally distributed. A. What is A? Tony Love. You're correct. They're all equal. It's normally distributed. And Karis, did you figure out B? Normal's only going to happen if they're all exactly the same. So we're just kind of looking at the mean and deciding if the mean is smaller than or greater than the mode and the median. If it's smaller than, that means it's going to fall to the left. So then B is obviously. Well, since 120 is smaller than 150 and 140, it's left. And then I saw some hands for the last one. Justin?
Right.
Correct. And the mean, again, is greater than the other two. If it's helpful, you have take a second. Write them out on a number line. So 75 in relationship to the others is higher. 60 is down here. And then the mode, 65, somewhere around there. But then it jumps out maybe a little bit more clearly that that is to the right of the other values.
What would we do if the mean was like in between the means and the mode? Like, if they gave you a number?
It's harder to tell, so you can expect if you're given a scenario like that it wouldn't be in the middle. Good question. Last example. A little refresher on z-score. So z-score formula, what is it? Who remembers? Anna.
Z equals X minus mu, is it?
Yeah?
Over 6.
Yes, from memory. Well done. So we have our z-score formula. Taking a look at this question, it says given this frequency table, talked about those at the beginning of Unit 2, for a population's data set where the standard deviation is 1.26, the mean is 8. Find the z-score for a raw score of x equals 9. That should sound familiar from yesterday's opener. Raw score is just a data point in a data set. So here we're talking about the ages of individuals and how many individuals are those ages. So there's 4 6-year-olds, 5 7-year-olds, and so on. It tells me that my sigma is 1.26, my mean is 8, and my x is 9. Just need to plug those in, calculate z. 9 minus 8 divided by 1.26. Common mistake here is to forget some parentheses here or calculate 9 minus 8 first, which you don't need to probably do in a calculator. So 1 divided by 1.26, what do we get? 0.79, and that is your z-score, which relates back to our standard normal curve, which is right here just above 0, and age 9 is above the mean, but not too far above, so we'd expect it to be right around there. It makes sense. And that's your last notes of Unit 3. Where x is a data point.